All right, let's go ahead and get started. First two should be relatively straightforward. It's just the usual inverse of a 2 by 2 matrix kind of deal. So here we would say that A inverse is 1 divided by, let's just calculate the determinant. 2 times 4 minus 1 times 3 is 5 times the matrix where you switch the 4 and the 2 and you change the signs of the 1 and the 3. I don't think there's any benefit to distributing the 1/5 there, but you certainly could write it as 4/5, -1/5, -3/5, 2/5, but I would leave it like that. Let's look at the next one. So B inverse here, again, is going to be 1 divided by the determinant, which is just 7, times the matrix where we interchange 7 and 1 and change the signs of 3 and 0. Now this last one here, we haven't talked about how to find the inverse of a 3 by 3 matrix, but this one you don't really need to know how to do it because this one's kind of special. So this is actually what an example of what's called it. Well, actually, I should back up. This matrix here is what's called an upper triangular matrix because everything that's on or above the main diagonal is, well, I should say everything that's below the main diagonal is 0. In a similar way, just to point out here, this matrix I'm about to write here, 1, 0, 0, 0, 5, 6, 1. It's not, oh my God, I was about to write it until I blew it. 0, 5, 0. Sorry about that. 1, 3, 4. This matrix is lower triangular because everything above the main diagonal is 0. Here, everything below the main diagonal is 0. So lower triangular, upper triangular. And this matrix here is diagonal, meaning that everything that's not on the main diagonal is 0. And diagonal matrices are really kind of special. They're really special because you can find their inverses super easily. The inverse here, you're literally just going to invert each of the non-zero diagonal entries. So we're going to get 1/2, 0, 0, 0, 1/3, 0, and 0, 0, 1/6. And the way you can check this is by actually multiplying these matrices together. If you multiply C by C inverse, well, this first row dotted with this first column is going to give you 1. And then this is a nice way of saying it. Whenever you take a row from C and a column from C inverse, if they're not the same row and column number, like if you do the first row with the second column or the first row with the third column where those indices don't match, you're going to get 0. First row, second column, 0, 0, 0. First row, third column, 2 times 0 is 0, 0 times 0, 0 times 0, 1/6, all zeros. But when the row number and the column number do match, like the second row and second column, you're going to have non-zero things matching up. And you'll get 0 times 0 plus 3 times 1/3 plus 0 times 0. So I'll give you 1. Same deal with the third row, third column. You're going to 1. So any diagonal matrix, you can find its inverse by just literally taking the inverse of the diagonal entries, as long as they're all non-zero. Cool. The reason I mentioned that is because I saw it come up in a couple people's web work problems. So I wanted to be like, oh yeah, we can do an inverse of an easy 3 by 3 matrix, but harder ones take more of a process that we shouldn't dedicate time to learning. That shouldn't probably the wrong word. That we're not going to dedicate time to learning because there's other things we have to learn. Let's talk about solving matrix equations a bit more because there is an important kind of thing we're leading up to, which I think we'll get to today. Let's see here. So let's see. Let's look at some matrix equations. Yeah, let's say we want to solve this equation. 2x, sorry. Yeah, I'll wait this way. 2, 1, 1, 3 times the variable vector xy equal to 7, 4. I would really like for all of you to get comfortable going between this and just writing it as a system of equations. So we should be able to rewrite this as the equations 2 times x plus 1 times y equals 7. And 1 times x plus 3 times y equals 4. These two things are equivalent to each other. And you certainly could solve this system of 2 equations and 2 unknowns relatively easily, right? You could take the second equation, multiply by -2, add the first one to it, cancel the x's, solve for y. Not that big a deal. But for reasons we'll see in a little bit here, it's really in our interest to talk about how you solve this using matrices, which is just to multiply both sides by the inverse matrix. So we're going to say, okay, well, if I call this matrix A, which is typical, A inverse is going to be 1 divided by 5 times the matrix 3, -1, -1, 2. I really feel like I should skip this next step, and I will for the next one, but here I'll do it. So then we take this equation and we multiply both sides by A inverse. On the left, we're going to get 1/5, 3, -1, -1, 2 times A, which is 2, 1, 1, 3 times xy equal to the inverse multiplied by 7, 4. So 1/5 times 3, -1, -1, 2 times 7, 4. Now, the reason I say this step is kind of unnecessary is that at least the left side, I shouldn't have to write out all of this because all of that, A inverse times A, is just going to be the identity matrix that is 2 by 2. You can check if you want, but you don't need to check. We know it's going to be the identity. That's literally the definition of an inverse. Is that when you multiply it by its inverse, you get the identity. So what this boils down to is we end up getting just the identity times xy. So I'll write that out. So 1001 times xy equal to 1/5. Yeah, sure. Times, let's multiply this out. 3 times 7 is 21, minus 4 is 17. And -1 times 7 is -7, plus 2 times 4 is 8. So -7 plus 8 is 1. On the left-hand side, 1 times x plus 0 times y is just x. 0 times x plus 1 times y is just y. On the right-hand side, I will distribute here. You get 17/5, 1/5. So the solution to the system of equations is that x is equal to 17/5 and y is equal to 1/5. A nice thing to recognize here is that specifically for a system of two equations and two unknowns, you can think of them as lines, right? 2x plus y equals 7 is a line in 2 dimensions. So is x plus 3y equals 4. And where they cross is the one solution where x is equal to 17/5 and y is equal to 1/5. In fact, it seems worthwhile to actually see it. So give me just a moment here. Move this over to where you can see it. Why is there 3 screens? Sorry. Apologies. One sec. So if we actually graph those lines, 2x plus y equal to 7 and x plus 3y equal to 4, and look at where they cross each other, you get exactly 3.4, which is 17/5, and 0.2, which is 1/5. So literally the solution is just where they cross. But what that means is you could have a situation where you had no solutions if the lines were parallel. Or you could have an infinite number of solutions if the lines were actually the same line. Just maybe they look a little different. So we're going to actually explore that a little bit more right now. I just wanted you to kind of see the physical evidence there. Let me get back to where my thing was. There we go. Cool. All right. So yes. Let's solve another one and then we'll talk about a couple of things. Yeah. Yep. So you all, well, in fact, yeah, you all should do one. You all should solve the system. To solve the system, we have 2x plus 3y equal to 5 and x minus 5y equal to 9. So first, write it as a matrix equation. You should start doing it. And then solve it by finding the inverse and then getting your solution vector x equal to A inverse times B. Give that a go. All right, here's what we've got. So the matrix equation, also called the coefficient matrix, or sorry, the matrix A, which is often called the coefficient matrix, is you're literally just looking at the coefficients of x and y written as rows, columns. That matrix times your variable vector x, which has like x with a little arrow over it, is just whatever your variables are, x and y in this case. We often use x1 and x2 instead of x and y, so we'll probably try and do some of that as well. Equals the vector 5, 9. We're going to find A inverse. It's going to be 1 divided by the determinant of A, which is 2 times -5 minus 3 times 1. And then we do the usual thing, switch the 2 and the -5, change the sign to the 1 and the 3. And then in this case, I don't love having a negative coefficient. That's just personal preference. So I distributed the minus sign to each of the terms in there and made it positive 1/13 times positive 5, positive 3, positive 1, negative 2. Not necessary, just style. So then second part, solving for x. X is just going to equal A inverse times our B, which is going to be our positive 1/13 times 5, 3, 1, -2 times the vector 5, 9. Be careful when you write, if you're me and you write 1/13, it often looks like you're writing 1 over B if it's me. It's because my 1 and my 3 get too close to each other. It's 1/13 times, let's see, 25 plus 27 is 52. And 5 minus 18 is -13. And look, that's going to work out very nicely. That's going to be 4, -1. So our solutions here is x equal to 4 and y equal to -1. You can go back and check that easily, right? 8 minus 3 is 5, and 4 plus 5 is 9. Yeah, that works out. Okay. So great. It's nice to be able to solve systems of equations like this. But really the reason we're talking about this mostly so that we talk about what happens when you don't have one single solution like this. So let's look at another example here. Keep things in track here. Also I'll point out in both of these cases here, A was invertible. And A being invertible essentially means you can only get one solution because your xy is going to equal whatever A inverse times your B was, right? There's no multiple options here. Again, this makes sense if you have two lines that cross each other. There's going to be one solution. But if your matrix A isn't invertible, we can't use this process. So for example, if I want to solve something like, or try to solve something like the system 2x plus y equals 7, let's make it real obvious, 2x plus y equals 5, I think we can all see, before we do anything else, there's not going to be a solution to the system of equations. There isn't an x and y pair that are both 2 times x plus y equals 7 and 2 times x plus y equals 5. Right? The same thing on each side can't equal two different numbers. So this system has no solutions. And if you look at the matrix in the matrix equation, it would have been 2, 1, 2, 1 times xy equals 7, 5. And we can't try to solve this the matrix way because we can see that our matrix A, right? Our matrix A is not invertible. What's the word for that? It doesn't have an inverse. It doesn't have a partner. It's singular or single. Yeah. So A is not invertible. It's singular. And if you look here, we can't solve this equation. I mean, I know I've said it like 3 times already. But we can see that the determinant of A, which would be 2 times 1 minus 2 times 1 is 0. So if A is singular, I should say, if A is non-singular, like in the previous examples, you're going to get exactly one solution. But if A is singular, that's not going to happen. You're either going to get no solutions because your lines are parallel, right? These two lines definitely are parallel. They look something like y equals -2x equals 7, so something like this. These are like our two lines here. They go through the point like 0, 7 and 0, 5. They never cross each other. Or you might have something like the equations, the system of equations, 2x plus y equals 7 and 4x plus 2y equals 14. And these, I mean, I don't actually know the definition. Sorry, I'm saying things I've already thought I said out loud. I'm like, let me answer the question I haven't even asked yet. But what I was trying to say is these lines are the same line. I don't know if that technically qualifies them as being parallel. I don't think so. I think you have to be different lines to be parallel lines, but it doesn't really matter. I shouldn't be going down that route. What matters here is that we have an infinite number of solutions in this case. Right? So try to solve the system of equations, well, there's a lot of solutions, right? Anything that's a solution here is also a solution here. Our matrix would still be a matrix that was singular. Right? This matrix A here, our determinant of A is still going to be 0. 2 times 2 minus 1 times 4. But in this case, the lines are the same, meaning there is an infinite number of solutions. Now be careful if you're ever asked about this, because I've seen students say like, oh, the solutions are all real numbers. No, that's not the case. There's an infinite number of coordinate pairs that are on this line. So the solution really is the line. Some examples of solutions here. The point, I don't know, any point on the line 2x equals 7. So like 3 comma 1 or 0 comma 7 or 2 comma 3, right? The list literally goes on. So why I'm stressing this is because in a bit, we're going to look at an equation. We're like, well, we're not very interested in the case where there's only one solution because the one solution isn't going to be very interesting. So that's why we're going to then say, oh, we really care more about the case where there's multiple solutions, which means the determinant of our matrix has to be 0. Because otherwise, if the determinant's not 0, the matrix is invertible, and the one solution we get kind of sucks. Whereas if the matrix is for real, like we don't care about that. So that's why we're building this up right now. And I think we have enough time to get there if we are hasty here. All right. So let me ask. So we're about to talk about eigenvalues, but let me ask you first. Have any of your instructors talked about like rotation matrices? Or good. I'm hoping the answer is no. If the answer is yes, that's also fine. So cool. All right. So let's move along. So the question I kind of wanted to start with here is what happens when we multiply a vector by a matrix? For example, when we multiply the matrix 2, -1, 1, 3 by the vector 1, 2, which I'll call A and V, what do we get? Well, we get, let's see, 2 times 1 plus -1 times 2 is 0. 1 times 1 plus 3 times 2 is 7. And let's call that W. So graphically, what's happening here is you're taking your original vector 1, 2, and it's both getting rotated and lengthened or shortened. In this case, lengthened. So there's our vector V. Here's W equal to A times V. Or in other words, when you multiply a vector by a matrix, it can change both the length and the direction. So matrix multiplication changes or can change the length and direction of your vector. And there's kind of a whole kind of discussion about how a rotation matrix doesn't change the length and just changes the direction. So for example, this matrix, and I will say it because it is worthwhile. I'm going to talk about it for like 2 seconds. R theta, the rotation matrix by an angle of theta, which is cosine theta, negative sine theta, sine theta, cosine theta, rotates a vector counterclockwise by an angle of theta, but doesn't change the length. So for example, if you were to take, say, a real easy vector like, I don't know, 1, 1, and a rotation vector through an angle of, say, pi over 4, which would be equal to cosine of pi over 4, negative sine of pi over 4, sine of pi over 4, and cosine of pi over 4, which are all root 2 over 2. If you multiply that by that, look what happens. So if you multiply, shouldn't have tried to write it more than once. Oh well, sometimes that happens. Look what happens when we multiply these together. I don't know why, this shouldn't be a minus on here, this should be a plus, minus, plus, plus. So root 2 over 2 minus root 2 over 2 is 0. Cool. And root 2 over 2 plus root 2 over 2 is going to be root 2. So look what happened. I took my vector that was pointing in the 1, 1 direction, the vector v, with a length of root 2, right? It's got a 1, and a root 2 is the hypotenuse there. And I rotated it 45 degrees or pi over 4 radians to end up with the vector 0, root 2, which has the same exact length, but has been rotated 45 degrees. Let's call that W. The reason I mentioned this is because it's kind of a nice counterpoint to what we really care about, which is the opposite thing. We're not looking for matrices that change the direction of a vector and preserve the length. We want matrices that preserve the direction of the vector and potentially change the length. So we're trying to look for matrices, although I'm saying this kind of wrong, looking for matrices where it'll preserve the direction of the vector. Or specifically, we're going to say that for any matrix, we can find a vector whose direction is preserved when you multiply by it. Let me show you an example. Somewhere in here. Yes. So let's look at this matrix. A equal to 3, 6, negative 1, negative 4. And V equal to negative 6, 1. And I will point out here in a second, observe that A multiplied by V does not change the direction of V. Let's take a look. A times V is 3, 6, negative 1, negative 4 times the vector negative 6, 1. And we're going to get, let's see, negative 18 plus 6 and positive 6 minus 4. That's going to end up being 12, 2, negative 12, 2, sorry. And if you look at that, that is exactly equal to 2 times the original vector, negative 6, 1. So what this matrix multiplication has done is it has preserved the direction of our vector, but it's lengthened it. So if our original vector, negative 6, James, really? You picked negative 6? Ugh, drawn this axis in the totally wrong way. Okay, fine. So if our original vector was, we'll make our scale real small here, negative 6, 1, then A times V just doubled it and gave us something pointing in the same direction, negative 12, 2. Cool. So some language here. For this matrix A, we say that V equal to negative 6, 1 is an eigenvector of A with associated eigenvalue lambda equal to 2, where the eigenvalue is just the scaling factor. So however much your vector got lengthened by or shortened by, that is the eigenvalue. I should say whatever factor it got lengthened or shortened by. So great, I just gave you a matrix and a vector and said it worked, but you can't just like pick any random vector and have this happen. It has to be a very specific vector based on the matrix started with. And there is, of course, a process for finding them in general. So the question really remains is, how do we find the eigenvectors and values of A, or of any matrix A? Well, let's talk about what we're looking for. We are looking for a vector so that if you multiply A by that vector, you end up getting a multiple of that vector. So here's what we want. We want A times the vector that we're looking for to equal some number times the vector that we're looking for. That's what we really, really would like to have. And here's how we're going to go about solving this. We're actually going to find the eigenvalues first because it's easier. Much, like I don't even know if you can do it by finding the eigenvector. I don't think it's possible to find the eigenvectors first if you're just starting with a matrix. I think you have to find the eigenvalues first. So here's how we're going to do that. We're going to bring everything to one side. So A times the vector V minus lambda times the vector V is equal to the zero vector. I will point out, although this general idea is true for larger matrices, 3 by 3, 4 by 4, any larger square matrix, we are in 2 by 2 land here. So when we write this here, we're imagining a 2 by 2 matrix times a 2 by 1 vector equal to lambda times a 2 by 1 vector. That's what we are thinking of almost exclusively in this situation. But the reason I point that out is because I would really like to factor a v out of this left-hand side of this equation. The problem is I can't really do that right now. So if you factor out a v, you're left with a 2 by 2 matrix, minus lambda, a number. And that math doesn't make sense. So to make it make sense, we're going to kind of add something in. We're going to say, oh, we're going to write this as a times v minus lambda times the 2 by 2 identity matrix times v. Still equal to the 2 by 2 zero matrix. Sorry, 2 by 1, 2 by 1, 2 by 1. That's a 2 by 1 over there. Right, this matrix over here is the matrix, the vector 0, 0. And now we can totally factor out a v. Now, with matrix multiplication, if you are trying to factor stuff out, the sides are important. I cannot write the v on the left-hand side if I factor it out. I have to write this as factor it out where v is on the right. And over here we have a minus lambda I. Still equal to the 0 matrix. Okay, here's where we're getting back to the thing I was saying earlier. I have an equation. I really want to find the solution to this equation where this is a 2 by 2 matrix times my 2 by 1 vector equal to this 2 by 1, 0, 0 vector here. And I really, 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 really don't want this 2 by 2 matrix over here, a minus lambda I, to be invertible. Because if this was invertible, I could multiply both sides by the inverse, and my solution would be not very exciting. So I'll just point out, if a minus lambda I is invertible, then we essentially get v equal to, let's just call it b for a second, v equal to b inverse times the 0 vector. But a 2 by 2 matrix times a 2 by 1, 0 vector is going to be a 2 by 1, 0 vector, right? If you've got something here times 0, 0, what are you going to get? 0, 0. And we don't like to think about that. We just don't really consider 0 to be an eigenvector, right? It's not very exciting. Like if you're the 0 vector to start off with, you're not really pointing in any direction. You're literally a point, which is kind of stupid. So to say that the 0 vector was an eigenvector, you're saying, well, yeah, of course. If you multiply any matrix by the 0 vector, you're going to get back a multiple of the 0 vector because you're going to get back the 0 vector. So it's just not a very interesting case. We don't care about that case. Great. So we want to look at the case where this is not invertible. But for a matrix to be not invertible, its determinant had better be 0. So what this boils down to is to find the eigenvalues. We're going to say, great, we want to solve where the determinant of this matrix, A minus lambda I, is equal to 0. And that will help, that will allow us to find the eigenvalues. And if you don't remember all that explanation, that's really okay. But I really did want you to know like why we are doing this. It's not just because someone made up some stuff somewhere. It's because like, oh, there's actually a reason. Like we want this matrix to not be invertible. That's why we want the determinant of this quantity to be equal to 0. Cool. Also, you're welcome to ask questions along the way if you have questions. I think this explanation is really kind of slick. Like, I'm like, oh, this is really. I'm always like, oh, this is a neat, really way of saying this. Yes, it totally makes sense. Sometimes. So then let's go back to the matrix we started with, the 3, 6, -1, -4 matrix. And even though we already saw from before what one of the eigenvectors was and the associated eigenvalue was 2, let's go ahead and find all the eigenvalues via the usual process. So we're going to find the eigenvalues, and lambda is typically the letter of choice for calling eigenvalues. To find the eigenvalues lambda the usual way. So we're going to start with the determinant of A minus lambda I. I don't think you, so here's what, I'll write out like 3 steps here, but I'm going to tell you which one I think you should actually write out. So it's the determinant of A minus lambda times the identity matrix. I would skip that step. I'd skip what I'm about to write as well. You could even imagine this as the determinant of our matrix A, and then distribute the lambda each of those and get lambda 0, 0, lambda. But what you should really start off with after you write determinant of A minus lambda I is just in each of the diagonal spots, subtract lambda. So in this spot and this spot, I'm going to have a 3 minus lambda and a -4 minus lambda. And in the other spots, just leave it alone. That's what you should always jump to if you're finding the determinant of A minus lambda I is just subtract lambda in each of the diagonal spots. So upper left corner, lower right corner. If it was a larger matrix, it would be, you know, all 3 on the main diagonal. All right, then we take the determinant. It's 3 minus lambda times -4 minus lambda minus 6 times 1, and we set it equal to 0. And then this will typically be a quadratic equation. It's usually going just to multiply it all out. If the problem has been thought out ahead, it'll usually factor. So if we multiply this out, we're going to get 12 minus 3 lambda plus 4 lambda plus lambda squared minus 6 equal to 0. And simplifying, we've got lambda squared plus lambda. 12 minus 6 is plus 6 equal to 0. That feels like I'm making a mistake somewhere. So I don't think that factors, and I know it should factor. Oh, it should be a minus 12. 3 times -4 is minus 12. Sorry about that. That should be a minus 18, not a plus 6. Let's just cross it out. Sorry about that. So we should get lambda squared plus lambda minus 18. I still feel like I'm making some stupid mistake here. Now I'm not seeing it. I don't feel like that factors, and I know it should factor because I know that one of the factors is. Let me look at my notes here. Let me see where I'm making a stupid mistake. Let me see if you guys can catch it. Oh, I'm real smart. Yeah, real smart. There's another mistake. Minus 6 times, I lost my -1 here. That's the problem. There we go. So good example of why it's important to be very careful because it's really easy to make small mistakes with the math. So let's write it out again. That should be a plus 6 here. One more time. Finally, we've got lambda squared plus 1 lambda minus 6 equal to 0, which does indeed factor as lambda plus 3 times lambda minus 2. So we get 2 eigenvalues, and that's pretty typical. You can get one eigenvalue repeated, like they could both be 2 or they could both be 3, but it's very, very common to get 2 distinct eigenvalues. So we get lambda equal to 2 and lambda equal to 3. -3, sorry. It's pretty typical to label them as lambda 1 and lambda 2. Doesn't really matter what we call them. So lambda 1 is 2, lambda 2 is -3. Great. After you found the eigenvalues, then you can find each of the associated eigenvectors. Let's go ahead and do the process for finding the eigenvector for lambda equal to 2, even though we already know what it is. So for lambda equals 2, here's what you do. Well, there's actually a couple ways to do this. I'll remind you, we're trying to solve this equation, a times b equals lambda times b. And so actually, I would just leave it with that. So I'm going to write the matrix A times the vector I'm trying to find equal to lambda times the vector I'm trying to find. So here's what I mean by that. We're going to write A times V equals lambda times V. So we're going to get our matrix A, 3, 6, -1, -4, times the vector V that we don't know what it is. I usually call it XY. Some people will go with X1, X2. I wouldn't use V1 and V2 because we're already kind of using V1 and V2 for the names of the eigenvectors. Because usually I'm actually calling this V1, this lambda 1, and this V1 here. And it's going to equal lambda 1, which is 2, also times the vector V1. There's all the labels. Let's zoom in a little bit, James. Okay, so now here's the nice part of this. You usually only need one of the two equations that this system represents. So you could write it all out. You could write out 3 times x plus 6 times y equals 2 times x, and -1 times x plus -4 times y equals 2 times y, but you only really almost ever need one of them. Occasionally the first one doesn't give you anything, and then you need the second one, but almost every time you can just look at the first one. If we look at the first equation, 3x plus 6y equals 2x. Subtract 3x from both sides. 6y equals negative x. And I would encourage you to stop there. Because at this point, you can pick x and y to be any numbers that aren't both 0 that satisfy this equation. And it's really, really easy to pick x equal to the coefficient of y and y equal to the coefficient of x. In other words, here, I'm going to pick my vector v1 to be x is going to be +6, y is going to be -1. Is it the same one I had before? Maybe. Does it matter? No. Well, let me double check. No, it's not the same. Right, before I had -6, +1. Is this also good? Yes, it is. Because any non-zero multiple of an eigenvector is also an eigenvector for the same eigenvalue. I could have said my eigenvector was, I don't know, -300, +50. And that would have also been valid. The standard or typical choice is to make it so that x and y are reduced as much as possible. So I wouldn't pick this because I could divide both by 50. But this choice or this choice, -6, +1, are both pretty standard choices. But any non-zero choice is valid. So you might all give different answers, and that would be fine. Well, actually, we already checked. I didn't check again. I was gonna say we could check to see that it works by doing a times v equals 2 times v, but we already know it does because we started off with that. Let's find the other eigenvector for lambda 2 equal to -3. Same process. For lambda 2 equal to -3, we're going to say that a times our unknown eigenvector, which we're calling now v2, is equal to lambda 2, which is -3, times again our v2. You don't need to label these things. I'm just labeling them so you can see what's happening. Again, I think you only need one equation here. If you just look at the first equation, you're going to get 3 times x plus 6 times y equals -3 times x. I'm going to subtract 3x from both sides, so 6y equals -6x. At this point, you could divide by 6, because why not? So y equals -x. So you could say that your eigenvector here is x equal to 1, y equal to -1. Or again, any multiple of that you like. Really, once you have an equation like this, you can just say pick x to be any number you want. It's not 0. And then find the corresponding y value. I picked x equal to 1. I got y equal to -1. So we found the eigenvalues and the eigenvectors for this matrix. It's a bit of a lengthy process. It's not one that's going away. This will definitely be present in 17C. You will find eigenvalues and eigenvectors of 2 by 2 matrices and use them to write solutions to systems of nonlinear differential or linear differential equations. It's not as bad as it sounds. It sounds like a lot, but it's really a relatively straightforward process once you get the hang of it. Questions about this before we do another one? Okay, we got time for one more because there's one more small thing I want to say about this. Assuming I can find where it's going to go. Yeah, sorry, I've just lost all my spots here. 1 second, sorry. Cool, there we go. Oh, yeah, if you do that. Right on. Let's look at this matrix here. Yeah, 2, 6, 1, 3. Yeah, sure, that's fine. So I'm going to do this relatively quickly here. So I'm going to go straight defining the determinant a minus lambda I, which is the determinant of, okay, here's the fast way. I'm just doing 2 minus lambda, 6, 1, 3 minus lambda. Find the determinant. It's going to be 2 minus lambda times 3 minus lambda minus 6 times 1, which is going to end up being equal to 0. And then we multiply this out. We get lambda squared. We get minus 3 lambda, minus 2 lambda for a minus 5 lambda. We get a plus 6 and a minus 6. So that simplifies down further as lambda squared minus 5 lambda equal to 0. Factoring, we get lambda equal to 0 or lambda equal to 5. Both are valid. 0 is kind of weird, but it does come up occasionally. So now let's find the eigenvectors. So one thing I want to point out is that I am more of a fan of finding the eigenvectors the way we just did it, where we did a times your eigenvector that you're trying to find equal to lambda times your eigenvector you're trying to find. But some other people prefer, and actually I should say, there are times when it's more advantageous to try to solve for your eigenvectors by using this equation. A minus lambda I times your unknown eigenvector equals the 0 vector. They will both get you to the same result, but I'll say that this other version, which we'll do right now, I think is better to use if your eigenvalues are really not nice. Meaning if your eigenvalues are irrational, like you had to use the quadratic formula and your eigenvalue was like 2 plus or minus the square root of 3. Or next quarter, if your eigenvalues are imaginary, which they will be, this is often the better way to do it because there's just less algebra to do. So we'll talk more about that next week. I'll do some examples with some less nice eigenvalues. But here, what that means for us is instead of doing like, say, 2, 6, 1, 3 times my unknown eigenvector equal to, let's do this one first, 5 times my unknown eigenvector. You could also say, I'm going to just solve 2 minus 5, 6, 1, 3 minus 5 times x, y equal to 0, 0. And both of those equations should get you to the same or similar enough eigenvector. Let's look at the first one. I have 2 times x plus 6 times y equals 5 times x. So 2x plus 6y equals 5x. I subtract 2x from both sides and get 6y equal to 3x. I divide both sides by 3 and get 2y equal to x. So x is 2 and y is 1. Or doing it this way, you get negative 3 times x plus 6 times y equals 0. So again, you're back in the same spot. 6y equals 3x, and then you've got essentially the exact same thing. So either way of doing this is valid. I would say I would generally default to doing it this way unless the eigenvalues were non-integers or even, yeah, if they're not rational. If they're irrational, like with square roots or imaginary, then I would definitely go this other way. I guess we should find the other one. So if lambda equals 0, which again is a weird eigenvalue, but it happens sometimes. Well, I should say it happens when your matrix is already not invertible, right? But this matrix here, the determinant was already 0 if you look at the original matrix. If that's the case, lambda equal to 0 will always be one of your eigenvalues. Kind of neat. So if we want to find, yeah, sorry, I have to, oh yeah, I'm going to do it the way I like to do it. So A times V equal to lambda times V. For now, lambda 2 equal to 0 is going to give us oh my God, I actually have to write out the matrix. 2, 6, 1, 3 times xy equal to 0 times xy. So in this case, we're just getting 2 times x plus 6 times y equals 0. It feels like it'd make more sense to use the second equation there. It's just I'm such a strong default to the first equation that I did. So this becomes 6y equals negative 2x or 3y equals negative x. So I'd say that my vector here is x equal to positive 3, y equal to negative 1. Last thing I'll say today. If this is my matrix, 3, 5, 0, 7. What are the eigenvalues? They're easy. They're 3 and 7. If you ever have a matrix that is upper triangular or lower triangular or diagonal, meaning you have a 0 here or a 0 here or both, your eigenvalues are always just the diagonal entries. Because look what happens. When you try to find the determinant of A minus lambda I, you get the determinant of 3 minus lambda, 5, 0, 7 minus lambda. And then when you actually take the determinant of that, you get 3 minus lambda times 7 minus lambda. But then having a 0 there or there means you're going to subtract 0. If you set that equal to 0, don't be foolish. Don't multiply this out. It's already factored for you. You've already got 3 minus lambda times 7 minus lambda equal to 0. So your eigenvalues, you've already found them. Your lambda equals 3 and lambda equals 7. So I'm going to say it again because it comes up more often than you would think. If you have a matrix where you have a 0 there or a 0 there or both, they're already telling you that the eigenvalues are whatever is on the diagonal there, which is great. Let me just say one more thing real quick. If this is the case, usually your eigenvectors are a little bit weird, meaning, check this out. I promise this will take like just a minute. I just want to show you this thing because it does always feel like it's kind of tricky to figure out what they are. So in this matrix, for lambda equal to, I don't remember which one's the weird one. So let's just do both. For lambda 1 equal to 3, if you have 3, 5, 0, 7 times the vector you're trying to find equal to 3 times the vector you're trying to find, we end up with the first equation, 3x plus 5y equal to 3x. What's going to happen to the x's? They're going to cancel. So what are you left with? 5y equal to 0. So y equals 0. And if y equals 0, what's x going to be? Better question. What is x not allowed to be? What did I say couldn't be an eigenvector? Both zeros. So if one of the coordinates is 0, the other one can't be 0. But what does it get to be then? Well, pick anything you want. Because if I pick 1, 0, and you pick 2, 0, and you pick 3, 0, and you pick 7, 0, they're all still multiples of each other. They all still point in the same direction to the right. So once one thing is 0, pick the other thing to be any non-zero number you like. The standard choice is 1. So here our eigenvector would have been the vector 1, 0. And then for the other one, just to finish it off, I know the other one's weird, but I do think this is the case where if you look at this equation here, 3, 5, 0, 7 times x, y equal to 7 times xy. This one actually, if you use the second equation, it doesn't help you. Right, so here the second equation just says 7 times y equals 7 times y, which is true, but doesn't tell you anything. Whereas the first equation tells you 3x plus 5y equals 7x. Subtract 3x, you get 5y equal to 4x. So we can say the eigenvector is going to be x equal to 5, y equal to 4. Lambda 2. The point of that was just to point out that if it was actually lower triangular instead, then the first equation wouldn't tell you anything useful, and you'd have to actually use the second equation. So that happens sometimes where one of the equations actually doesn't give you anything useful, and you have to use the other equation to find the relationship for the eigenvector. But then what I say is to remember that if you get a 0 for one of the things, just remember that the other one gets to be whatever you want, but everyone picks one. Nobody's original. Have a lovely few days off. I'll see you all on Monday.